The last 2 days I showed you how to find the electric field from a point charge, so just a single charge or a couple charges out in space. And tonight is all about how you find the voltage of a point charge. Now this is very simple because voltage is a scalar, which means we don't have to worry about the direction of it. We're not going to have to do any vector addition or anything like that. However, we will have to include the sign positive or negative, which might seem strange because you're used to positive or negative meaning a direction. In this case, a positive voltage means that it came from a positive charge, and a negative voltage simply means that it came from a negative charge. But they will still add, so if you had positive 1 volts and negative 1 volts, you add those and you get 0 volts. So we will include the sign because that lets us know, 1, what kind of charge we started out with, and because the voltage from a negative charge can subtract or cancel out the voltage from a positive charge. Now this is the equation for voltage, K, Q over D. Let me show you where that comes from because it really shouldn't be surprising. So electric field is, of a point charge, is K, Q over D squared. We did that the last couple days. And voltage is electric field times distance. Therefore, voltage would be K, Q over D squared, that's E, from a point charge, times D. And you get D cancels one of the D's, K, Q over D. Being inconsistent about capital Q or lowercase q, as long as you know Q means the amount of charge, it's not a problem. The units for voltage are volts or joules per coulomb. So it tells you how much energy is stored in that electric field. All right, so volts or joules per coulomb for voltage. And voltage, when I say voltage, is electric potential. And that's kind of that, like delta H in PE equals mgh. And someone asked me, is height then gravitational potential? And it is. Just like voltage, potential energy for voltage, Q times V, or delta V. V is that potential. So we're talking about the same V as we were at the beginning of the unit when we looked at potential energy is Q times electric potential. All right, make sure you know that equation, make sure you know those units, and that it is a scalar. If you do not know it's a scalar, direction doesn't matter, that can come back to bite you. Voltage questions are actually usually very easy. Electric field questions a little harder because you got to worry about magnitude and direction. But with voltage, you just figure it out and then add them together. Let's take a look at some examples. A positive 4Q charge and a negative Q charge are located at 2 corners of an equilateral triangle with sides of length L. What is the voltage at the third corner? So let me try to draw an equilateral triangle. We'll see how good I can do at it. And at one corner, we've got plus 4Q. And another corner, we've got a negative Q. Now, if this is truly an equilateral triangle, it won't matter what corner we put it at because it's all symmetric. No matter how you rotate that triangle, the distance between any of the charges would always be the same. So now I want to know what is the voltage at the third corner. So I want the voltage right here. Well, all I've got to do is figure out the voltage from each charge and add them together. Like I said, voltage is very, very simple. The problem tells me that the length of each side is L. So that means the distance in the equation for voltage would be L. All right, I'll color code this just to make it easy. Let's call the 4Q the blue charge. So voltage from the 4Q charge is KQ over D. And in this case, Q is K4Q. And just to keep in the habit, that is a positive according to the problem, positive 4Q over D. And that can be kind of weird because with electric field you just found out, well, we're going to worry about direction ourselves, so the negative or positive doesn't matter so much as long as we keep track of directions. With voltage, negative or positive matters very much. And that D is L. Could have went ahead and subbed that in. So now we've got positive K times 4Q over L. All right, now the voltage from, let's call this other one the green charge. So V from the negative Q, KQ over D, which will be K negative Q over L. And now we want the total voltage. We'll just add them together. So we'll take the voltage from the 4Q and the voltage from the negative Q equals, all right, positive, and I'm going to go ahead and put the 4 out front because it looks like I'm going to be adding and subtracting them. So I'm going to put the 4 out front, 4KQ over L, and then plus this next one, I'm going to move the negative out front, is negative KQ over L. Somehow I'm noticing my L down here became a 4. I don't know what's going on there. It's an L. And now when I add positive 4KQ over L plus negative KQ over L, that will give me 3KQ over L. Convince yourself, take a moment to convince yourself that's right. Notice that the distance between either of the two charges is in fact L, since this is an equilateral triangle. 4 minus 1 would be 3. Okay, if you don't understand that, take a minute to convince yourself that this is in fact the correct voltage, and then we'll move on. All right, here's a problem that's going to involve some graphing again. A 9 millicoulomb charge is located at coordinates negative 2 centimeters 0. Okay, so we need to set up a coordinate system. I'm going to just label this point here as my origin, and then do a little dotted line to help people understand where the x's are. So that's my y-axis. Here's my x-axis. And I'm going to call every, let's just say every 3 boxes 1 centimeter, because it looks like I'm only going out a couple in each one, and I don't want this to all get squished together. All right, coordinates negative 2, 0, so 1, 2, 3, that's 1 centimeter. 1, 2, 3. That's a 9 millicoulomb charge at coordinates negative 2 centimeters, comma 0. And I said every 3 boxes is 1 centimeter. And I just made that up. So it would be spaced out, not all squished together. And a negative 4 millicoulomb charge is located at coordinates 1 centimeter, 0. So 1, 0. This question is going to go easy on us. Don't have to do any kind of weird Pythagorean theorem to get the distance. If the charges, say, were out here not directly on the x and y axis, to find the distance, you would have to use Pythagorean theorem. But since we don't have one like that, we just got these two. Negative 4 millicoulombs at 1 centimeter, comma 0. All right, so now I just find the voltage from both and put them together. What might be tempting to you here is you might want to call this distance a negative, but distance is a scalar, and negatives and positive on a distance would only be meant to indicate direction, because distance is total no matter your direction, so you would never have a negative distance. You'd have a negative displacement, but not a negative distance. And you might wonder, but wait, voltage is a scalar too, and it can be positive and negative. Yes, because that indicates whether your charge was positive or negative. It's not about distance. And so voltage is a weird scalar, because it gets to be positive or negative. Okay, so once again, just for the sake of keeping everybody sane, I'm going to color code this. We'll call this the orange charge. Let's start there. I want the voltage from the orange charge relative to the origin. So voltage is K, Q over distance. In this case, we are given numbers. So K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Q is 9 times 10 to the negative 3. Milli would be negative 3. Over the distance, 2 centimeters, which would be 0.02 meters squared. So I get the voltage from the orange charge at the origin would be 2.025 times 10 to the 11th volts, or joules per coulomb are also acceptable. And now let's call this other one the purple charge. So the voltage from the purple charge is KQ over the distance. And that is 9 times 10 to the 9th Newton meters squared per Coulomb squared. and negative, remember, always, always, always include the positive negative for voltage. Negative 4 times 10 to the negative third coulombs, millicoulombs, at a distance of 1 centimeter, so from there to the origin. That should have been 3 boxes based on what I said earlier, shouldn't it? So if we put it in the right place, there's where our purple charge should be. Divided by 0.01 meters squared. And I get the voltage from the purple charge is negative, because the charge was negative, 3.6 times 10 to the 11th volts. And then I simply add the purple and the orange to get my total voltage. So voltage at the origin would be the orange one plus the purple one. So I do my voltage at the origin is equal to 2.025 times 10 to the 11th volts plus negative 3.6 times 10 to the 11th volts. And I get, I'm going to round just so the decimals don't get kind of crazy, negative 1.58 times 10 to the 11 volts. All right. Our voltage from the negative charge was clearly stronger because our voltage ended up stronger. And there we go. That's how you calculate the voltage.